Good afternoon, ladies and gentlemen. I'm here to talk about the MPS, and for some of you this may be very strange because me talking about flicker photometry, because I'm the one always saying reflectometry that you should be. The reason I'm here is that Scott McGrady should have been here. He was filling in for Ian yesterday, but I'm, well, having his talk actually. But in comparison, I will throw in some reflectometry also. I have no commercial interest whatsoever with this, so I'm not in favor of any method. I just come to comment what I know of this instrument and trying to explain to you, and as far as I understand, how this works and what may be the advantages and disadvantages. So this is a macular pigment. We are all familiar with it. And you know that flicker photometry, I'll just give a brief introduction because it makes sense for the understanding. Makes use of the fact that blue light is absorbed by the macular pigment and green light is not. So what you do in flicker photometry, at least in this device, is you flicker in a fashion the blue light and the green light off and on. And you can imagine that if you, the idea is that you know something. In the case that you see the flicker that's equally bright, the bluish and the greenish light source. And obviously if you have a lot of macular pigment, you need a lot of blue light coming in to reach this at your photoreceptor levels, whereas you have less macular pigment, then you need less blue light to come in to reach this level at your photoreceptor level, which is the actual detector. So by changing this distributions, you can imagine that you get a number for the macular pigment. So that's what's been done in flicker photometry. On this axis is the blue-green ratio. Here is a lot of blue, here's a lot of green. So you come in at a certain frequency and you flicker, and you see it flicker. Then at a certain point, you don't see it flicker anymore, because at this particular stage, your macular pigment matches as such that your blue-green ratio is equally perceived. And whereas if you then add on more blue light, you see it flicker again. So the idea is to find this particular point. And the flicker photometry in general, you change the blue light or the green light or the ratio, so you scan along this axis. Well, the MPS comes up with a different paradigm, but it wants to find, obviously, this same minimum point. So what they do is they start off at a certain blue-green ratio, start off flickering at a very high flicker frequency, so you don't see it flicker, and the flicker frequency is ramped down, and if you wait long enough, at some point, blue, green, you see it flicker, obviously. So at some point you see it flicker. But then if you come more to this point where you have your macular pigment, you will have a harder time to see it flicker. So at a lower frequency, you see it flicker, and the idea is just press a button as soon as you see something flicker. That's a task. And that's, as far as I'm concerned, a very easy task to do. You just sit down, and whenever you see something flicker, push a button. And you're not aware where being in this, on this graph. So this is how a particular measurement looks like. Here is the blue-green ratio, a lot of blue, a lot of green, and at some point you see a minimum. And this is an actual measurement which has been done by me. This is me, having 0.38 yesterday at the very room downstairs with the MPS2. The measurements I'm going to present to you are made on an earlier version, but that's only a software update as far as I'm concerned. The measurements are exactly the same. So you ramp down, you push the button, and then you do it for several blue-green ratios and try to find this minimum. Obviously, you have to then do a peripheral measurements, as John pointed out correctly, because you don't know how your green, what your detector is doing, your green ratio, and your lens density obviously also influences this. So you have also to do a kind of peripheral setting at 7 degrees, at 8 degrees, where you assume the macular pigment to be absent, and then it's just the width, the tween gives you a number for the macular pigment optical density. So this is like how all the flicker photometry works. This is with the MPS. There's some graphs to show that it really does the trick. Oops, I'm sorry. This is as a function of exercity, the macular pigment optical density as measured by the MPS. This is a test retest. This has been shown before by others, so I included this also. Oops, I'm sorry. And we did this some time ago, and we found an 11% difference between test and research in a perfect correlation. This is in the Netherlands. And these are measurements done in Singapore recently. And they came up with a new device, having a new software update, and they came up with an even better result, which is comparable to what others find. This is a database from a lot of subjects showing that the distribution that they find more or less looks what has been found in literature. Hold on, and this is a comparison with Billy Wooten's device, which has been used in John Nolan's lab. And again, we see an excellent correlation as far as I'm concerned. So whether you measure with the MPS or the Wooten's device, the correlation is okay. It means having a high macular pigment density on one machine will give you a high density of pigment measurements on the other machine. And the absolute values, they may differ because, well, the actual widths maybe differ a little, but that depends. It's for all the setups which are available. You must use them within a setting, but to compare different machines, that's always tricky. Okay, what was the meaning of this? I don't know. Oh, yeah. So this is going from the central to the periphery. And then less macular pigment is there, so you need more bluish light in going from here to there. If your lens density would increase, then you would also expect a shift going to the right, and that's exactly why you need this peripheral test, because you cannot rely in principle on this measurement only. So if you would do measurements at several different subjects aged differently, then you see indeed a shift to the right. Here are actual measurements. Here are some measurements with different ages, and you see this shift. And what the MPS, is the software now tells you, and you may debate on it. Please don't ask me if this is correct or yes or no. This is just what comes out. This is an estimate on the age only, and this is if you do add the peripheral test, and it seems to correlate very well. This may be normal, not diabetes, not these particular subjects which you need. So you may question this. You can argue that if you want this test in a kind of intervention trial, then it's okay. But if you want to compare different subjects, then this may be arguable, as far as I'm concerned. So this is results from one particular optometric practice, and these are results from from a lot of subjects, and they correlate well. So, as I said, if you want to do it within an interval, I guess it's a good guess to only use the center measurement only. Okay, now it's stuck. Let's try this one. How can I go forward? Oh. Okay, the software update also included some measure quality index to be sure that you have a proper measurement. As soon as the measurement it's too noisy or people don't understand, then you get a kind of quality index so that you can reject the measurement and do again. So now about reflectance. That's a technique which has been developed in the Netherlands. And I will later on compare it with this flicker photometry to come back to this flicker photometry. What's reflectance? Well, that's actually what you do as an ophthalmic doctor. You just look into the eye and you look how much light is reflected. And instead of being a doctor looking, oh, this is a white there, or this is black, I'm a physicist, we try to have numbers with this, go along with it. So this is what it comes out. Here is the wavelength, bluish, greenish, reddish. Here's some light which is reflected out of your eye. You see there's a lot of reddish eye, which we all know. And the next graph which I'm going to show is exactly the same measurement. The only thing which is different is it's a linear scale, and here it's on a logarithmic scale. And that's because I want to look in more detail at this particular region, because this is a simulation with a subject having no macular pigment at all. But if you would have macular pigment, less light would be reflected in this region because macular pigment absorbs, and it would look like this, or having more macular pigment even like this. So only changes in this area. And as was already pointed out this morning by Leopold, we have come up with a model to model this reflection. Lens density is one of the parameters, macular pigment is one, and some more others. But macular pigment definitely is one, and if you do then look at actual measurements, these are the dots here, the squares, we can fit this straight line and have a model, a parameter, an estimate, taking into account the actual lens density, so no H estimate whatsoever, the actual lens density, and measure macular pigment density. These are examples from 2 studies we did. This is another example, and which was measured yesterday. We also looked, since we are able to have lens density, lens optical density also, with the same device. We also did this study 10 years ago where we noticed that lens optical density is lower, so better, so to speak, when you have a higher macular pigment optical density. So lenses don't age that fast if you have a high macular optical density. Okay, the technique we started off with, well, Leopold showed you the actual setup, but we now have and this is really it's Jan van der Kraat. This is Jan. He's retired now, but he developed a small device which enables us to do this in an undulated eye within a second, having a reflectometry measurement. With here's again a test-free test, which is very good, 7% test-free test results from this device. And we were even able to improve it a little bit further. We heard yesterday there are slight differences between lutein and zeaxanthin. And one of the differences is that there's a slight wavelength shift of 10 nanometers. This is lutein and zeaxanthin separately. And we make use of this by looking at this actual slope. And we hoped to be able to discriminate between lutein and zeaxanthin in vivo. So how can I convince you that we come up with numbers which make sense? Well, the first thing obviously you have to do is look at the distribution. We saw, John showed this L to Z ratio, so a lot of Z. Zeaxanthin at the very middle, or mesozele, and lutein at the periphery. So if you actually measure with our device, we should come up with things like this. And this is what we actually measured. So different eccentricities we measured. This is the lutein distribution, and this is the zeaxanthin distribution. So that makes sense that we're actually measuring what we hope to measure. We then did another test. We supplied supplements, 3 supplements with zeaxanthin. And if you do so, you expect zeaxanthin peak to go up, whereas the lutein peak would stay the same. It wouldn't be wise to supplement with lutein because this conversion, they would both go up. So this is what we found. Here for the 3 subjects, this is the lutein. We supplemented with lutein. These are the lutein results. These are the zeaxanthin results. So zeaxanthin increases, lutein does not change. There's one thing to be noticed before I continue on this slide. We supplemented for 200 days, and then we stopped. And what we noticed is that the zeaxanthin optical density is increasing, even if you stop with your supplement. So somewhere in your body must be a store which enables zeaxanthin to continue accumulating in the eye. We never noticed this with lutein supplements. As soon as you end your supplementation, at least in our trials, serum levels and macular pigment levels tend to decrease. Not that, maybe not that fast, but they go down. They never start to increase. Unfortunately, I have no measurements beyond this. Okay, this is the baseline measurements, and these are the follow-up measurements. Lutein does not increase, zeaxanthin does increase. So as I said, this can be measured in seconds. You just sit down, and then you have your measurements done, and you get at a certain eccentricity, at a certain field width, 1 degree, these numbers. Okay, we then have so I come back to the heterochromatic flicker photometry again. These are our values, these are the MPS, and they correlate quite well. These are from another data set, same MPR, MPOD, but they quantify, so that's the MPS1, but actually the same hardware as the one as you saw below, same number. So we confident that both machines measure something alike. And this is the third data set which we measure, and we also see a correlation. In this particular experiment, we also measure the different exercities, and then you see that it's a deviation if you go to the black squares, which is the central measurements, whereas it's more alike at more in the peripheral sites. And we try to come up with a model to explain this, so to really understand what's the cause of this. So now it gets a little bit more complicated, and I hope I can get you through. The squares are the actual measurements, lutein, zeaxanthin, as I showed you before. What we're measuring when we say 0 degree, that's not 0 degree, that's an average over a 1 degree field. So if you have a steep distribution, you can imagine that the actual point at 0 degrees, your actual measurement at 0 should be higher, because this point is in fact an average over a 1 degree field. So what I did is I modeled it with a Gaussian distribution, assuming a Gaussian distribution for the zeaxanthin and for the lutein, and calculated what underlying distribution would give me the actual data points I did measure. So then this is the zeaxanthin, lutein, and the actual macular pigment optical density. So that's the underlying optical density of the macular pigment. And I then tried to use this blue line to understand the psychophysical measurements. So for a start, psychophysical measurements, they assume at 8 degrees there's a 0 point. There isn't. There's also a small offset, 0.04, 0.05, but there is. So you should, you should shift your black squares a little bit up, as we did here. And then at the very center, you also come up with a problem. But that is because if you do psychophysical measurements, you most probably null your flicker, or points the button when you see something flicker, not in the very center, but somewhere around the edge. So when you say it's a null degree measurement, you actually have, depending on your width of your measuring, you're actually measuring at 0.7 degrees. So if you put in both, then you actually you can actually put the two on top of each other. So let me then summarize this with these two statements. I hope I explained to you how the MPS works, that it's a device which gives similar results than the routine device, let me say the ordinary flicker photometry, and that it compares well with optical techniques like reflectance. They both have the advantages and disadvantages, and I'm happy to discuss this with you now or afterwards with a drink or whatever. Thank you.
Thank you very much. Are there comments from the audience?
A comment to begin with, and that is that, as you probably recall, John Landrum and I also looked at the continuation of macular pigment increase beyond the supplementation period.
Okay.
With lutein.
With lutein.
Yeah, we found the same thing.
You found the same thing?
Yep.
Okay, but also for that long time period?
Yes. Mm-hmm.
Oh, okay, and then yeah. how much lutein did you supplement with?
30.
30, okay.
That was the first study.
Okay.
Now, my question concerns these graphs where you're comparing one technique with another.
Yes.
And yes, you get a correlation.
Yes.
But you can look at two people who have pretty much exactly the same measurement on one machine, but vastly different values on the other machine. And I wondered if you had some comment why this.
I don't understand. But when you
Well,
compare
for example, on the MPS,
yes.
you might get two people who have got an MPOD of 0.4.
Oh, yeah, I can comment
But on
on-
the other machine, one of them is 0.2 and the other one is 0.8.
That may depend on the distribution. I mean, if you have a very peak distribution or you have a broad distribution, that may give you a similar result on one device, but different result on another device. You have your peak distribution, so that might be the underlying cause.
Toss. With your finding that the macular pigment tends to rise or can rise after stopping supplementation,
Yeah.
you at least have to be careful about invoking, and a lot of people invoke this, about invoking peripheral stores or some stores that are being mobilized, because the serum has dropped.
Yes, it
and
is.
so there's no way that the eye will know that the serum, what's going on in the fat or anything else. It only knows what the serum
well,
is.
we did not do serum measurements for this particular
Yeah.
experiment, so that's it really.
Well,
Yeah.
I'm sure the serum has dropped if you've stopped your supplementation.
Probably not. No.
So it either is a change, either it's a change in the binding proteins, and I would accept that if there's some way that that's happening, or else it's an artifact. It can't be. You can't say that it's mobilizing stores or it's coming from some unknown source.
Well, the only thing we notice is that it's kept on going
Right.
beyond the period where we supplemented with Zeaxanthin, and it
Yeah.
was only Zeaxanthin,
Yeah.
only which kept on going.
And so.
And if I do if I would do a placebo, it wouldn't show up anything. I mean, didn't show you, but
Yeah.
many measurements.
Yeah. Well, you have to. Yeah.
Relative to that, what if it is coming out of adipose at the same rate that it's going into eye, for example?
You would never know. The eye has no
But
idea.
the serum levels.
The serum levels have dropped down to
Yeah,
very
there
low.
There could be a mechanism, I can imagine,
Yeah.
a regulatory mechanism, which is
That's-
increasing mobilization from
Yeah.
one tissue to another where the serum levels don't necessarily markedly change.
It would be very unlikely. I'm a pharmacologist. From pharmacokinetics, that's not the way things work. In the
Maybe
body.
there's something to. We have 3 subjects. You don't need that much subjects to give it a try.
Yeah.
Just supplement somebody for 2 months with Zeaxanthin or meso, and then stop and one of your students as a volunteer and so, and then.
So I have another question, and I
Sure.
don't know, this would be an easy one for you to test. What if I were to give you just a mixture of lutein and zeaxanthin
Yeah.
in a cuvette, using your models, how accurate can you actually tell me how much lutein and zeaxanthin would be in that mixture, as opposed to looking at HPLC, which clearly is the gold standard?
Well, we can give you numbers for the eye.
Yeah.
Yeah.
No, but I want to know just in the cuvette, because that's
In a
a
cuvette.
challenge. That's
Okay.
That's why
Yeah.
HPLC exists,
Okay.
because it's hard to separate lutein and zeaxanthin.
That's a challenge. Shall we? Let us. That in 2 years' time, we'll be able to tell you when we meet again.
Yeah, I'd
Yeah.
just be interested in seeing that,
Sure.
because it's all depends on your models. You don't even know the lutein and zeaxanthin when it's bound to binding proteins. It may
I
shift.
agree with you that the numbers, you may disagree on the absolute numbers, but then again, these results that you come up with distributions which look what you expect, that's
Yeah.
so these numbers make sense.
Okay.
Toss, just one further comment on the
Yeah.
on the previous point, and that is that when John and I did our study, what we found was that the macular pigment density stopped increasing at the same time, pretty much, as the blood serum level had come back down to baseline. Because it took about, with that 30 milligram dose, it took about, John, what was it, 30 days to get back down to baseline? I mean, it came back down with a sort of
Yeah.
exponential decay, but by the time it reached baseline,
The serum
that was
levels.
when the macular
Yeah.
pigment stopped
Yeah,
increasing.
I guess that's what I also find with lutein, but that's, well, unfortunately, we did not have the serum levels for the things. We should have done this, but maybe that's an experiment to be done. Yeah. But may have implications, though, because the actual messages, if you have a load, maybe you don't need, at least for Zeaxanthin, that high of a doses ongoing if this is true.
Okay, any further questions? One more.
One quick question, and I
Sure.
apologize, it's not going to be as brilliant as the presentation. And I don't even know if you can answer it because this is
Give it
not
a try.
your device. MPS2 now takes fovea and paraphobia.
Yes?
MPS1 has been used for years, only took fovea.
No, no, no. The measurements I showed you were all foveal compared to the measurements I
They were
showed
both
you.
available.
No.
We were told that you only need to take one.
Listen, all the measurements I showed you were done in my lab, and
With
that's
both. I'm telling you, MPS1 in the practical world, we were told to take only one.
that could be. So I showed you because I've got the slides from this 50,000 subjects comparing the central and the central only and both measurements. But the comparison with the psychophysical, psychophysical technique and the reflectance, that's done by the comparison because I did it myself.
I know, my
Yeah.
question is, what do we do with all the measurement we took when we were taught to only take one?
It's a good question.
Yeah.
Yeah, that's the
my
same what
question.
John
See?
asked.
I
Yeah.
told you I would have a good question
Yeah,
before
I
this.
guess my answer would be if you if you use it in an intervention trial, then I think you can look for changes, because changes. Well, what you actually do having a peripheral measurements is to compensate for differences in optical density of the lens, and I don't think within a year time this will change that much that it will influence your actual MPOD estimate compared to the changes you want to pick up by a supplement. If you want to compare different subjects with different ages, then you should.
compare a patient in 2011, 2012,
Then I guess you are allowed to do, as far as I'm concerned, to have your central measurement only, because it is a within subject, and the idea is that the peripheral measurements will more or less be the same. But I'm not the expert, but that's what my opinion.
Frederick, I think it would depend in part on how far out you're measuring. You know, we've certainly seen folks who, if you just look at their central measure alone, they look like their macular pigment is going sky high when they supplement. But what you notice is that their parafoveal measure is also going up a little bit too.
Yeah.
So you have to, I mean, if you look just at the central alone, you'd have an idea that they were lutein rock stars.
Yeah.
And then when the parafoveal is considered, you find actually, no, that was a tenth of a log unit change over an entire year of measurement.
No. My explanation would be there is indeed a rise in the peripheral also too. So what you do is you underestimate your actual central measurements in having
But not every subject does that.
Okay, but not every subject has a broad distribution. There are differences. So what you should do is then have the subjects measured on, well, maybe the best on our device or with the No. I'm not in favor. No. Let me explain. Because we come up with actual measurements. We don't need a reference. You could also use the autofluorescence technique from Heidelberg or of others, which gives you an actual distribution. But they also use some reference point at 7 or 8 degrees. So you end up with the same problem. So indeed, it may be that you have some changes at the peripheral, but I think that's because of the supplementation too. That's not an actual change in your, let's say, your phi lambda curve, which would be the only cause.
So I just wanted to make a few points of clarification. One is that when you're making the peripheral, using the peripheral reference, you're not just correcting for lens density. You're also correcting for retinal sensitivity, which can vary a lot, and in fact can vary according to an intervention.
But will that change with intervention?
Yeah. Well, we have a lot of data suggesting that macular pigment is also related to retinal sensitivity.
Okay.
So that you'll miss that.
Okay.
The other point is that a lot of times in your second slide you showed that when you make the blue measurement and the green measurement, that you're doing it like a line. So when we say macular pigment optical density, we're saying we're implying that that's macular pigment optical density at 460 nanometers, as if we measured it with a laser.
Yeah.
But all these devices, use light sources with varying wave bands. And so this is why we can't use a monitor to measure these things, because the wave band is so high that you get a lot of zeros in your data that you can't mathematically correct. So what happens with all these devices is, and even, like I said the other day, within a device, is the wave band is differing all over the place. And then you add in these lower wavelength densities to your 460, and that changes the absolute value all over the place.
So you're also in favor of my reflectance techniques, I understand. Comments.
Well, I was suggesting earlier, one of the issues I think that with reflectance, and you're the master here, but there's a little bit too much look up the answer in the back of the math book problem. So when you model, you're modeling, you're using a lot of values in your model based on sort of known spectral characteristics of the pigments, and so you're correcting to get that spectrum. So consequently, but you're not measuring the spectrum and then using that to validate your method.
Well, that has been done, measuring the spectrum by comparing a foveal and a parafoveal measurement spectrally, and then subtracting them. You get, well, I can show you not now, but maybe tomorrow. You just see the macular pigment coming up.
That's what I was mentioning, though. The problem is all those things vary in individuals. And it's similar with the lipofuscin method. I mean, the lipofuscin autofluorescent method assumes a sort of homogeneous univariant distribution of lipofuscin that's not changing.
No, not necessarily. That's why you need to have a green reference to just also take out the lipofuscin distribution.